Hi everyone. In today's video we are going to go over example 3.7 from Digital Design and Computer Architecture, the ARM edition by Harris and Harris. The question is stated as, is the circuit below combinational or sequential logic? Explain in a simple fashion what the relationship is between the inputs and the outputs, and also what would you call this circuit. So the circuit that's given to us looks like this. There are two NAND gates, and their outputs are fed back to their inputs. So they're cross-coupled NAND gates. And they've labeled the inputs. There are two of them. One of them is S bar, the other one is R bar. The outputs are Q and Q bar. So before we begin this problem, the first thing I'd like to do is to just remind ourselves how the NAND gate operates. So recall for the NAND gate that this is its truth table. So you have two inputs, and you AND the two inputs first, and then you invert whatever your result is. So what you see in this table is that the output of the NAND gate is going to be 1 whenever either of the inputs, A or B, is 0. So to put that into text, whenever either input is 0, the output must be 1. And to say that slightly differently, whenever the input is 0, it will force the output to be 1. So the first thing we can do, when we look back at the circuit that we were given in the problem, is to note that we have two inputs. So we can list all the possible input combinations first for S bar and R bar. And we do that here, S bar, R bar. So with our 4 different input combinations for those two inputs are listed. And then the first thing we'll try to do is to list all of the forced outputs for Q and Q bar. So remember that Q is the output of the NAND gate that takes S bar as an input, and Q bar is the output of the NAND gate that takes R bar as an input. So let me scroll down, and let me just draw really quickly on here so that we remember that S bar feeds into the NAND gate that outputs Q, and R bar feeds into the NAND gate that outputs Q bar. Let me just scroll up to confirm that. So R bar, yep. So what we said earlier is whenever there's a 0 on either of the inputs to the NAND gate, the output of the NAND gate will be forced to be 1. So what we do in the first part of this question is to just fill out all the locations that we know will be 1. So because there's a 0 here, in this location here, Q bar therefore would be 1. Since S bar is 0 here, Q would be 1. Since S bar and R bar are both 0, Q and Q bar would be 1. So that was the first step. We labeled and populated the output as much as we could based on what we know the output would be forced to. And then from there we start filling out the rest of the table. So we'll start by looking at this row, the second row. From earlier we figured out that this 1 would be here. So now the question is, what goes into the Q bar? What is the Q bar output when we have this input combination? So we'll look back at our circuit, and again we're trying to figure out what Q bar is. So there's Q bar, and this NAND gate takes R bar as an input, and R bar in this case is 1, and the other input to this NAND gate is Q. So we figured out that Q is 1, and we said from earlier for the NAND gate operation that when both inputs are 1, the output is going to be 0. Therefore, this Q bar output is necessarily 0. And you can see that it's the reversed case, or the mirror image, when we're on our third row. Since it's just a symmetrical circuit, you would expect that the output for Q in the third row would also be a 0. So now we've populated 3 of the 4 rows. We've made it to our final row. And so for the Q output, when S bar and R bar are both 1, we can't say for sure it's whether or not it's a 1 or a 0. Specifically, we can't say for sure that it's a 1 because neither of these inputs are 0, which would force the output to be a 1. So what I've gone ahead and done is just list out how to compute what Q would be when S bar and R bar are 1. And so it would just be the computation NAND of S bar and whatever the previous value of Q bar was. So again, remember that Q is the output of the NAND gate that takes S bar as an input. Similarly, Q bar is the output of the NAND gate that takes R bar as an input. Therefore, Q bar would be the computed value of NAND of R bar and the previous value of Q. So we look one line down now, and we see that I've replaced S bar with 1 and R bar with 1. And the reason why I've done that is because I'm looking at my inputs, and for this specific case, S bar and R bar are 1. So I've replaced S bar with 1, and I've also replaced R bar with 1. And now there's just 2 unknowns in both of these equations. It's Q, the previous Q bar and the previous Q. So I've listed out all the possible combinations of Q previous and Q bar previous from 0, 0 all the way to 1, 1. So at this point, it's just a simple computation of the NAND. So again, whenever either input is 0, the NAND will have to be forced to output a 1. So you work through that logic, and it results in a truth table that looks like this. And so before we move on any further, remember that this whole computation on the left is to figure out what the current value of Q is, and this computation on the right is to figure out what the current value of Q bar is. So that's all I've denoted down here. Instead of current, I wrote new, but same meaning. The first thing, or the next thing to notice is that the new value of Q and Q bar is not the same as the previous value of Q and Q bar. And this happens for both the final row as well as the first row, where the new values of q and q bar do not match the previous values. Since they do not match, we call these unstable states, and the reason they're unstable is because essentially the circuit would keep flipping between the new and the previous values, and it would never really converge to any specific state. That leaves us with the two states, or rather the two rows in the middle, where the new values of q and q bar do match the previous values of q and q bar. And since it does match, it tells you that these two states, when the previous values of q and q bar are 0, 1, and 1, 0 respectively, that the NAND function as it's computed in this circuit will result in a stable circuit. So the key point to take away is we don't want to ever be in a case where we're in the first row, where q prev and q bar previous are 0, 0, and we also don't want to be in the case where they're both 1, 1. And to just think about, if we just look at this from a higher level, q and q bar, they should be complementary anyway. So by the way that the question was designed, it sort of hints at the idea that these two values should be complementary. To finish up here, we'll just quickly notice that for the two states that are stable, the new values of q and q bar are equivalent to the previous values. So 0, 1, 0, 1, and 1, 0, 1, 0. So I've gone ahead down here and finished populating our truth table for the circuit, the original circuit, and I've just written q previous and q bar previous. So what this tells us is that the circuit that we've been analyzing thus far is in fact sequential, specifically because when you're in the state where S bar and R bar are both high or 1, the output depends on what the previous values of q and q bar were. So before we finish up here, the thing to take away is you don't want to be in this first state, because we said earlier that we want to make sure that q and q bar are complementary to each other. We don't want them to be either both 0 or both 1, and in this first row, q and q bar are both 1. Specifically, the reason why we said we don't want to do this is because it's problematic if you go directly from this state, this first row, to this final state. And again, if you make a transition from this first row to this final row, you're going to get an unstable circuit that's going to keep bouncing between two different sets of values. So if we take a close look at this, we notice that this is essentially an inverted SR latch. What that means is it's an SR latch, as depicted in this symbol here, but the inputs to the S and R are inverted. So there's a bubble to symbolize that right in front of the S and R inputs. So to quickly show an example of that, remember that S stands for set and R stands for reset. Normally in a regular or typical SR latch, if the set bit is high, then Q would be set high, and Q bar would therefore be set low, or reset low. R similarly would reset the value of Q to 0. So in this case, the bar means that the set functionality is active low. So if we look, we'll ignore the first row because we're not supposed to do that, and we'll start looking at all the other rows. So again, active low for the set and reset signals. So when S bar is 0, Q should be set high because it's being set high. Set means to make something high, and reset means to make something low. Similarly, again, active low. So when R bar is 0, Q should be set back, or reset rather, to 0, and that's what we see happening here. And then when we get into a state where S bar and R bar are both 1, then Q and Q bar, those outputs will retain whatever the previous value of Q and Q bar were. Okay, thank you.